We've talked about simple probability, calculating simple probability. We've calculated, or we've talked about how to calculate if one or another event happens. Okay? And that was involving the addition rule. Now we're going to talk about situations where we multiply. Okay? And when we multiply, it involves conditional probability. And a condition itself represents a given in a problem. In probability, we would use a vertical bar with two events beside each other. So how this would read is, what is the probability of A given B? Or in other words, what's the probability of A happening given that B, some other event, has already happened or has already occurred? And we're back to the OkCupid example. Okay, and we saw in a previous lesson that we could use a table, we could use a Venn diagram to represent this situation. But remember, there were basically two events that we pulled out of this. Probability of randomly selecting a tall person and the probability of randomly selecting a high earner. Okay? So I won't go over, it's the same, exact same example, exact same numbers. Here, it's shown in a Venn diagram, where we've got a circle that represents the tall earners, or sorry, the tall men, and the other circle that represents the high earners. So as a review, what would be the probability of selecting a tall man? How would I find that from this Venn diagram? Sorry? So this one plus this one? Yeah, because both of those are in the tall circle over the total number, which was 192, right? That was the total number. And we get 123 out of 192. Now this one you got to be careful with. What is the probability of selecting a tall man given that he's a high earner? 101 out of 101 plus 48, or 149. Because this is the probability of tall and high earner out of the total number of high earners. Okay? So just as I said that, the probability of selecting a tall man, given that he's a high earner, would be the probability that they're tall and a high earner over the probability that they're a high earner. And it would work out to this, which would be 101. Notice the denominator changes now, 149. Because we're not counting all of them now. It's only out of all the high earners. That is the conditional probability formula. And this is another one like the addition rule that you will get. You'll always get that. So what's the probability of A happening given that B has happened? It's the probability that they both happen divided by the probability of B happening. Okay, so given means divide by the given. Okay, same example, but this time we've got the two-way table. First question is the same as the first question in the Venn diagram. Probability of a tall doesn't change, right? It's 22 plus 101, or we could just have used the margin total, 123 over 192. Okay. But as soon as we have a condition or a given, our denominator is going to change. It's not going to be the entire population. In this case, 192 men. How would I calculate, if you think about this formula, the probability of selecting a tall man given that he's not a high earner? Or in other words, given that he's a low earner. That would be the same as saying not high earner. How would I calculate that? Well, it would be the probability of both of them happening together over the probability of a low earner. So tall and low here, right? 22 over total low, 43. So, I mean, a lot of times it's common sense just from looking at the Venn diagram or the table, or you can follow the formula. Okay. Independence. When we do multiplication with probability, something called independence comes up. As in, are two events independent of each other? So two events are independent if knowing the outcome of one event does not affect the other event. Have a deck of cards. This I find is usually a good way to explain it. So I'm going to shuffle it. I'm going to draw a card. What's the probability I draw a king? 4 out of 52. So let's say I drew a king. Where's the kings? Can't find a king. There's a king. Okay, so I found a king. Put it back in. Shuffle again. What's the probability that I draw a king? 4. So those events are independent, right? The first event did not affect the other. Okay, restart. What's the probability I draw a king? 4. So I draw a king and I keep it out. What's the probability that I draw a king now? 3 out of 51. Those are not independent because the second event depends what happens in the first, right? If I draw a king, there's a certain probability for the second one. If I don't draw a king, there's a certain probability for the second one. It all depends on what happened in the first. Okay? So, the probability, two events are independent of each other if the probability of A given B is equal to the probability of, sure, I got this right. Get this, yeah, probability of A. So going back, selecting a tall man who's a low earner. We always already calculated these. Selecting a tall man was probability of T on the previous page, which was 123 out of 192. The probability of selecting a tall man who is a low earner. So the probability of tall, given that they're low, which means not high, was 22 out of 43. Now, when we're testing for independence, a lot of times it's good to go to percent or decimal. Okay? Because I need to know if these are equal to each other or not. And it might be difficult to see in fraction form. So if I converted that to a decimal, I get about this. If I converted this one to a decimal, I get about this. So if they are not equal to each other, they are not independent. One does depend on the other. So I would simply say, to test for independence, you would just say because PT does not equal PT given low earner, they are not independent. And that's sufficient. That's all you have to say. Okay? If we look at the actual proportions, we can see that the probability of selecting the probability of selecting a tall man, given that they're a low earner, decreases, right? So it changes depending on whether it's a high earner or low earner. In this case, low earner, it goes down. This final thing with independence, last lesson I talked about mutually exclusive. Two events that could not happen together. A lot of students think, well, mutually exclusive events must be independent of each other. They seem to make that reasoning. Here's why that's not true. Okay? Here we have two mutually exclusive events in the Venn diagram. They're mutually exclusive because they don't overlap. Okay? What's the probability of A happening? 0.8, right? 0.80. What's the probability of this happening given that this has already happened? Think about it. 0. Doesn't make sense. So because these are not equal to each other, they are not independent. Okay? So mutually exclusive events are not independent. Think of it this way. If I put actual events here, and this I'm going to go back to the male and pregnant. So let's say that this event is selecting a male. And this event is selecting a female who's pregnant. Obviously, both can't happen at the same time. So what's the probability of selecting a male in this situation? 0.8. What's the probability of selecting a male given that they're pregnant? Come on. Doesn't make sense. 0. Okay. So knowing that one event occurs greatly affects the probability of the other event. In fact, it decreases it to 0. So, like we talk about independence when we talk about conditions, conditional probability. We talk about mutually exclusive when we talk about or, when we use the addition rule. Okay? Like they're really two separate things. So just as a summary from this, and remember in the previous lesson, I told you that or means add, and means multiply. And you can see here, for all events, okay, this is if they're dependent events. One depends on the other. To find the probability of two events happening, I have to multiply the probability of the first event by the probability of the second event, given that the first event happened. If the two events are independent, one doesn't affect the other, I just multiply the two probabilities together. That's it. Okay? So there's lots of different questions that can be asked. Okay? Let's look at one such type and how we can go about answering it. Because a lot of times, a certain method can help us answer certain questions. Okay? And obviously, we see we're going to do a tree diagram. So we have two things happening here. We have a 0.65 probability of getting a higher than average GPA and ACT score. So that's the first event. Do we get higher than average or lower than average? And then the second event, well, if it's higher than, then we have a certain chance of getting admitted to a college, to a school or university. Okay, if it's below, we have a certain chance of getting admitted. So best way to tackle these types of problems is with the tree diagram. So the first event that's happening is we either are higher than average or lower. Let's fill in the probabilities on the other side of these branches. So what's the probability of having higher? So therefore, what would be the probability of having a lower? Yes, 0.35. If you wanted to change it to percent, I suppose you could. I'm going to leave them as decimals. Okay, so let's say higher happens. Well, if we have a higher, then two things could happen. We could get admitted, or non-admitted. What's the probability we get admitted? 3.3. What's the probability that we don't get admitted? 0.17, because you have to take it away from 1. If we have a lower than average GPA and ACT score, again, two things could happen. Maybe I get admitted, maybe I don't. One would think that the probability of getting admitted would be lower here. And it is. You only have a 0.39 chance of getting admitted if you have a lower than average GPA and ACT, which means what's the probability of getting not getting admitted? 0.61. So when we have situations like this, we want to fill out the tree diagram with the probabilities. Because then we're going to use all these numbers to help us answer certain questions. Okay. What is the probability of getting a higher than average GPA and getting admitted? How would you find that? According to the tree diagram, what would I do? Multiply these two. Okay, it would have to be 0.65 times 0.83. Because it's the probability of it being admitted times the probability of being admitted given that I have a higher than GPA, higher than average GPA. So that gives us about, just give you that one, approximately 0.54. Or sorry, yeah, that's this one. You got to be a little careful with. What's the probability of getting admitted? How many scenarios are there in this tree diagram where you get admitted? 2. So you have to calculate the probability of each one and then add them together. So half one could be high, then admit. And that is the one we just did. 0.65 times 0.83, which gives us approximately 0.54. But then there's also another path. There is a path that if you have a lower than average GPA ACT, you get admitted. And that is 0.35 times 0.39, which gives us about 0.14. So therefore, admitted is 0.54 plus 0.14, which is going to give us 0.68. And we need these two pieces of information to answer the third probability question. What's the probability of having a higher than average GPA ACT given that you've been admitted? Well, that would be the probability of both of them happening together. This is according to the formula, over the probability of the second one happening. So you can see I have to take this answer to there and this answer to there. So it would be 0.54 over 0.68, which gives us approximately 0.79. So just as a summary, because we basically finished the probability rules, we're just going to look, we're going to have one more lesson where we look at a couple of probability situations. Okay, and then we're going to move on to something else that probability relates to in stats. But if you just sort of think about these ones, you know, you want to have some kind of reference to work from, whether that's a Venn diagram, a two-way table, a tree diagram. Remember your complement rule. Remember that OR means add, given means divide, and means multiply. Okay, those are sort of the general rules that you've got to think about when you tackle probability, because like I said, there's all sorts of probability questions you can be asked.